Hello. In the previous video, I have explained the required assumptions and implicit assumptions for the classical linear regression model. And that was just an introduction, a recall. I just, as a reminder to you, because I would like to introduce a more general concept here. But still the example is the classical linear regression model. So I'm going to explain some abstract concepts. So I want you to match those abstract concepts to what you see from the classical linear regression models. So first, what I'm going to explain here is actually not commonly recognized definitions. So it's my understanding, so my framework. I'm not sure how many econometricians share the same definitions like this, terms. But I believe it's natural enough. So let me try. What I want to do here is I would like to distinguish the model and the method. And you can find it from the Wikipedia. So this concept is less discussed, not well taught in many textbooks, but I believe it's very important. So let me explain. When I introduced you the classical linear regression model, remember I have done it in several steps. First, I told you the basic assumptions. So we think about a linear function and it satisfies these kind of assumptions. And then the next step is to think about how to estimate the parameter of interest. And we know that there are like MLE, OLS, GLS estimators. So basically there are two different steps in those in this introduction. The first part is about the assumptions. That is the econometric model. So the classical linear regression model consists of 4 assumptions plus implicit assumption, basic assumptions. So the set of those assumptions is referred to as an econometric model. So a model is assumptions, right? On the other hand, based on those assumptions, you need to think about how to recover or how you utilize the data, right? The ordinary least squares method is about computation and how to use the data. So that is the method. So the OLS estimator utilizes the assumptions and the data. And so the process of combining the assumption, utilizing the data and the assumptions will be referred to as an econometric method in my course. It's my terminology. I believe it's intuitive enough. The definition is intuitive enough. So simply, so from the linear regression model, it's clear. So that previously, so when you say, okay, we will consider an OLS model, and we are going to estimate that with a regression method. This statement is rigorously actually wrong. So I think the correct statement is that here we are going to consider a regression model, linear regression model, and given the model, we can estimate that by an OLS estimator, right? So when you refer to a model, it is about assumptions, and when you refer to a method, it is about like algorithm and how you utilize the data. So distinguishing these two, I believe is important. Because why is it important? It's like because later you are a PhD. I don't teach this concept to undergraduate students. I think they are not able to understand this, and they don't need to understand this because the major difference is a PhD. When you get a PhD, then basically your job is to think about new method or criticize other methods or learn others' methods and utilize them. Then the main problem here is say you are doing some data work for your employer, and then Suppose that you encounter a problem. Then from the problem, you have to solve the problem. That is your job. You are an expert in data handling, data analysis. So then the first step, the many students are confused at this point because you have to diagnose where the problem is coming from. There are two types of the problems. First, your problem may be coming from the model, which means your assumption may be wrong or you don't have enough assumptions. So in this case, if the problem is coming from your assumptions, some of your assumptions, then it is not a problem about the data. No matter how many data you have, you are not going to get the correct answer. Your answer will be wrong. So even if you have an infinite number of data, but if your assumption is wrong, then your analysis will be totally wrong. So then you have to study why your method is not, your model is not correctly working. On the other hand, if the problem was coming from the method, then you have to think about your data or your program. So your model is correct, your model is general enough, correct enough, strong enough, but you don't get, you encounter some problems, then there may be computational problem, or your method is not efficient enough, is not accurate enough, or your data may not be enough. The sample size may be too small, or there may be like other unknown problems such as missing values you could not recognize, or some typos that you did not recognize. Those kind of problems are related to the data, so you have to fix that problem on the data side. So diagnosis is important because otherwise, so if the data problem was from the data, then it's not a problem of the assumption. Even if you change the assumptions, still you are not getting the correct answer at all. So telling the distinguishing those two concepts will help a lot, I believe, later if you see some more challenging problems. So that's why I'm introducing you those distinctions. And in this chapter is about identification. And the identification in this chapter, we will study the econometric model. So econometric model is what we study in this chapter, and econometric methods or estimators or hypothesis testings will be studied later. So in other words, in this chapter where we study the econometric model, we don't care about data. So we don't care about data we assume that their data have no problem. So otherwise, or in other words, we will assume that conceptually, we will assume that we can have as many data as we want, say infinite number of data. So still there are some problems. There are some problems, some cases where infinite number of data do not help. Even if you have an infinite number of data, you may not be able to do anything because your assumptions have some problems. That's the problem we will consider in this chapter. And usually that said, the parameter is not identified or not correctly identified. So when you have an infinite number of data, if you could estimate the parameter or if you could obtain the correct conclusion, then we say that the model is identified or the parameters are identified. However, they may not be identified, so that means infinite number of data will fail. So then that's identification failure. This is conceptual distinctions. Then let me briefly describe what an econometric model has to define, what it should specify. First, it has to define what is random and what is not. So you may think it's obvious, but actually it's not. So in a linear regression model, we know that x, y, epsilon are random. When I say random, that means different individuals will have different values. So if you choose a random individual, or if you choose one random individual and another person, their observations may be different, then it's random. But the parameters beta or sigma squared is the variance of epsilon given x. So the variance parameter and the coefficient, slope coefficient, are assumed to be constant. So non-random. They are not random. That means everyone has the same value. So if you randomly choose a person, no matter who you choose, it must be the same. And in contrast, there are other models where those assumptions are relaxed. So for example, if the slope is random, then that is a random coefficient model. If the variance is random, that is a stochastic volatility model. So they are used in different contexts. And they become different models. So specifying those is important. And second thing we need to learn from a model is that you have to define what variables are observed, what's not. Of course, also in the linear regression model, it's obvious. Epsilon is not observed, x and y are observed, and beta are not observed. So, like in a simple model, it's obvious. But let me give you more examples where there are some unobserved variables, not observed variables, in a irregular way. So, this example, random utility model. Suppose that you have to decide whether you go to college or not. So it is 1 or 0 decision, going to college or not. And economists usually model this decision in this way. Assume that there is a utility u of I is individual i's net utility when she chooses to go to college, right? And we assume that the utility is a linear function of x and epsilon. And however, the problem is obviously the utility is not observed in our data. What we observe from the data is whether you go to college or not. So the observation is only college or not and x, characteristics x, like your test scores, your family background, your parents' education level, and things like that. So observing x and c, what can we do? Can we identify beta without observing u? That is a very interesting and important model, and many of you may know this, like binary choice model, random utility model, discrete choice model. There are different names. So we call this, in other words, we call this latent variable. It's hidden, it's not observed, so it's latent. So these kind of models are common in econometrics. Now, another example here is measurement errors. Suppose that the true regression model we would like to study is this. We want to study the relationship between your wage and your intelligence. However, intelligence is an abstract concept. How can you measure that? True intelligence is not observed, or it's measured with errors. So instead of intelligence, we use test scores, your econometrics grade, for example, or like IQ scores. Still, anyhow, whatever test scores you use, it will have some kind of errors, randomness. It may not be correct measure of intelligence. So we assume that the wage is determined by your true intelligence, but the true intelligence is measured as x, but it includes a measurement error u. So true intelligence plus measurement error is your test score, and you only observe test score, but cannot observe the true underlying intelligence. This is another example. Okay, I'm going to go to the next step in the next video. Thank you for watching.